Good morning, everyone, or good afternoon, I guess it is. Thank you for joining us for hose selection and troubleshooting part 2. We have a good 30-minute presentation for you, so we're going to go ahead and get started. So most of you, all of you will be muted, and you can leave your cameras off to make sure we have the best quality. If you have a question, please use the chat feature. Hopefully your name is entered in that. But if it's not, please add that as well so that we can follow up with you if for some reason we don't answer your question during the session, but we should be able to get to all the questions towards the end of the webinar. If we run a little bit long, we will still take time to answer as many questions as possible. Your presenter today is Doug Nordstrom. He's the current product manager for hose products with Swagelok Company, 25 years experience, worked in a variety of areas within Swagelok, and has an extensive education in engineering that you can see listed here. Go ahead and take it away, Doug.
Thanks, Jen, and thank you everyone for joining our part 2 of hose selection and troubleshooting. If you missed the first part, no worries at all. We can reach out to your Swagelok contact and we can send you that material if you'd like. But at this session, we're going to go through and reiterate the importance of proper hose selection, and then go through a 4-step process that we stress in how to spec in the right hose for a particular application. And we're going to go through the 4 steps listed here one at a time. And at the end, we'll have time to go through a couple quick examples. And like Jen said, we'll try to answer as many questions as we can during the half hour. So first and foremost, and I've mentioned this at the first session as well, proper hose selection is a critical aspect of designing any fluid system. A lot of times it is an afterthought, which can be extremely dangerous. The analogy I like to use, it's like planning for the maintenance of your tires on your car. The tires are obviously a wear item, just like a hose. And so if the hose is not spec'd in properly, it can be extremely dangerous, first and foremost, but it can also cause expensive downtime, wasted product, and of course, maybe expensive environmental damage. So what we say here is really failure is not an option. The proper hose always needs to be really thought through and spec'd in for every application, and then planned for maintenance throughout the life cycle. Different things to consider. Some of these are obvious, but some may not be quite as obvious. Like with any fluid system component, we always want to look at things like pressure, temperature, and flow rate. Those always come to mind right away, but a hose is different than most other fluid system components that you might be used to because it has some other features that need to be considered when selecting the proper hose. The first maybe is a little more obvious than the others, which is chemical compatibility. A hose has a lot of internal surface area and is going to see the media, is going to be in contact with the media for long stretches, much more so than a fitting or a valve or a filter, regulator, what have you. So chemical compatibility is a critical aspect so that all that surface area is designed for seeing the media that is flowing through the hose. Something else that a hose is more susceptible to is permeation. Again, a hose has a lot more surface area than other fluid system components, and so permeation is a direct correlation to the amount of surface area the media sees. And in gas applications, a hose can permeate quite a bit, and so the hose needs to be designed to minimize permeation when that's important. Of course, a hose needs to be drainable. Some hoses are more drainable than others. And then, of course, we get down to the bending of a hose. Most hoses are very flexible, and there's 2 factors that need to be considered, and usually only the bend radius is what's considered by most people speccing in a hose, but the force to bend is very important. We've seen hoses that have a very small bend radius. You can bend a very tight bend, but it takes an extreme amount of force to get to that bend radius. It's a very different aspect. Likewise, there's some hoses that have a large bend radius. They kink relatively easily, but you can get that bend radius very easily. They bend very, very easily. And what this causes, of course, is a very kinkable hose because it doesn't take much force to create a bend radius that's going to cause a kink. So these things need to be considered and looked at when selecting the right hose. And then also, how's the hose going to be used? again, many times a hose is used as a bit of an afterthought. We've seen hoses used as a handle to pull doors open and close. That's going to cause a lot of damage on a hose. It needs to make sure that we see what it's going to be rubbing against, abrasion issues and potential kink points, so that we know how durable and how robust the hose needs to be when we decide which one's right for that application. So moving into the 4-step process, we like to basically say we're designing the hose, or we're speccing in the hose from the inside out. And so this is intended to be a cross section looking down the center of a hose, just a quick drawing of it. And what we're looking at is from the inside out, we have the core tube, which is going to be what touches the media flowing through the hose. The core tube then needs to be reinforced because it doesn't hold much pressure on its own. And so there's different reinforcement layers that can be put in place, and those need to be considered. Are they right for the application? And then there's various covers. Some hoses aren't covered, so sometimes the step 3 here is skipped, but many times a hose is covered. And we'll get into what these covers are intended to do and why you should use one sometimes and not others. And then, of course, what's not really included in this little diagram is the end connection. Basically, what kind of ends are needed and how are they put onto the hose and how robust is that connection. So diving into the first one, the core tube, the most important thing here is what is the material? And there's various materials that are readily available in different hoses, but this is going to be what really determines how well the hose is going to get along with whatever media is flowing through the hose. The 4 we have listed here are very common. A metal, so the actual core tube that we point to here is metal. This particular one is a Teflon core, but it could be metal. Also nylon, and then rubber hoses are very common. There's other materials out there as well, but those are 4 of the most common. And then there's essentially 2 different designs. A convoluted design that you see in this picture and a smooth bore. And they each have their advantages and disadvantages. And actually the convoluted design, there's really 2 different types of convolutions. This one is what we call a helical convolution, which gives it drainability. And there's also what we call an annular convolution, where the convolutes are all basically side by side. It's not a helical shape. So again, the core tube is the innermost material in the hose. It's the wetted surface, and it's going to be what sees the media. So the most important thing here is really this 3rd step. It must meet the chemical compatibility requirements. So is the metal going to corrode over time? Is it going to have hydrogen embrittlement? Is the Teflon going to get along with whatever media is flowing through? And then also, whether or not it's going to be a gas or a liquid plays into consideration for what kind of core tube is needed. But again, the core tube, and we test a lot of our hoses at Swagelok to see what the core tube withstands. And an average core tube can withstand only about 30 psi. And it's different for each one, of course, but only about 30 psi until the core tube bursts without any reinforcement on it, which is about 2 bar of pressure. So again, it's a very, very weak part of the hose, but it's the most in contact, of course, with the media. So reviewing those same 4, some quick advantages and disadvantages. We start on the left with a metal core hose. The 3 reasons we see metal core hoses used are wide temperature range. Of course, most of the time this is 316 stainless steel, and it's going to be rated up into the 400-ish or higher degrees Celsius, 800 degrees Fahrenheit, because that's, metal stays a strong material throughout a wide temperature range. It also essentially eliminates permeation. There is some gas molecules that will permeate through metal, but it's at such a low rate, it's really not really measurable by our permeation testing. And we've never seen an issue where metal hose permeation has been a problem for anyone. So really, it eliminates essentially permeation. And then vacuum applications, a metal hose can be rated down to a millitorr, which is essentially a 99.9999% vacuum. The convolutions of a metal core hose give it a lot of hoop strength under vacuum, and it can withstand a very, very strong vacuum, where these other hoses will only withstand about a 90 to 95% vacuum, about 28 inches of mercury if you use that that type of measurement. But the negative of a metal hose is like a paper clip. Bending a hose back and forth made of a metal core will eventually fatigue and damage the hose. Again, all hoses are wear items. And pressure impulses, so pressure spikes. Imagine if you open up a ball valve and thousands of PSI are subjected to the hose very quickly. Those pressure impulses will damage a metal core hose much faster than these other types. So those are things to look for if a metal core hose is needed. Teflon or fluoropolymer hoses, great chemical compatibility. Typically they're smooth bore for cleanability, but they can be convoluted, which give increased flexibility. We'll get into this in part 3, but an issue that Teflon hoses can see is something we call static dissipation. They can have static charges build up on the inner core, causing leaks when the static dissipates through the side of the hose. But there's ways around that, and so we'll get into that in section 3 of our talk. But there's ways that you can use a Teflon core hose that will dissipate static on its own. The downside, of course, is that Teflon permeates. And when you have a Teflon seat in a ball valve or Teflon seal, wherever it might be in your system, usually that's a very small amount of surface area, so the permeation is minimal and not really an issue. When you have a 10-foot hose, the permeation through a 10-foot hose with thousands of PSI in it can be quite extreme. It could be liters per hour type of permeation. And this will be a topic we dive into a bit more in the 3rd section of our webinars as well, but it's something to look for when needing a Teflon core hose. Nylon hoses were designed essentially for hydraulic and pressure impulses. They're very durable and they can take pressure impulses very well. Where the metal and Teflon also doesn't take impulses very well. Nylon core and rubber core are much more durable and will withstand that much better. The downside of both essentially is they have a lower temperature range. So they have high durability, but the softer materials don't allow for a higher temperature range, and rubber also has a relatively low pressure range as well, where nylon can get thousands of PSI pressure ratings. So again, the 2 different core designs, especially with Teflon, this is what we typically see with Teflon. All metal core will be convoluted in order to give it flexibility. If you imagine a very thin metal tube that's not convoluted, it's going to kink instantly. But a Teflon core won't kink right away if it's smooth bore. But adding the convolutions will add quite a bit of flexibility. You can tell from bending a hose just on the outside without looking into the core if it's a convoluted Teflon core or a smooth bore. Obviously the smooth bore will drain easier than the convoluted core, but be less flexible. So that's the trade-off. When creating the metal core convolutions, these diagrams here are intended to be a close-up picture of the metal core convolutes. And typically what is done when creating a metal core is rollers move around the outside of a very thin tube, about 10 thousandths thick, pushing into the tube and creating these convolutes. The issue with that is that it creates stress risers where the rollers are pressing into the thin tube, and it also puts twist into a hose, and those are 2 ways to really cause damage quickly. A mechanically formed metal core hose will not withstand as much bending and dynamic movement as a hydroformed hose. The way a hydroformed hose works is we pressurize the inside of the core tube, and on the outside there's a form in the shape of the convolutes, and the metal stretches and forms into the convolute shape. The advantage of this is it eliminates any twisting in the core, so there's no torsion stress, and it greatly reduces the amount of work hardening. Everywhere inside of that core sees the same amount of stress as it's being formed. And these hoses will last much longer in dynamic cycles. The downside is it takes longer to make, therefore usually hydroformed hoses are going to be more expensive than mechanically formed. So again, you have to understand how the hose is going to be used, what kind of dynamic motion is going to see when deciding how which hose to apply to an application. Moving on now to the Teflon, a little more detail on permeability. I think most people probably know, but permeability is gas molecules flowing through Teflon. There's holes in the Teflon when it's extruded, and gas molecules just flow right through the Teflon. We did some testing with a standard Teflon core 1 foot hose. At 3,000 psi, it permeates about 2 liters per hour at just a 1 foot hose. There's a baking process that we can do, hose manufacturers do, that we call slow sintering. And what that is the Teflon core, after it's extruded, goes through a oven. It basically flows through an oven like a pizza in a pizza oven. As a pizza goes in one side and moves through and comes out the other side, it's cooked. That's what this slow sintering process does. And that sintering process tightens the bonds between the Teflon and drastically reduces the permeation rate by it's in the neighborhood of 7 times less permeation that you'll see in a slow sintered hose. A post sintered hose is even sintered further. As the tube is extruded, the entire tube is then put into an oven, similar to baking a cake this time, and it's heated and baked and then allowed to cool. We call that a post-sintering process, and it tightens the bonds even further. And from the original Teflon extrusion tube, we see about 1/40th the amount of permeation in a post-sintered hose. So again, post-sintered, the advantage, of course, is it's the best for a gas application to minimize permeation, but it's going to take the longest to make, and therefore it'll be a little more expensive than the other types. So moving on to now pressure impulses. What we mean by a pressure impulse is a very rapid increase or decrease, for that matter, in a high amount of pressure inside of a hose. So this again is like opening and closing a ball valve, where a pressure cycle or a pressure surge is a slower process, similar to opening or closing it. A multi-turn needle valve would cause a pressure cycle, for example. Pressure impulses will damage metal hoses especially very, very quickly. The hydroforming I mentioned earlier withstands this much more because of there's the great reduction in stress risers in a hydroformed hose. So a pressure impulse application, with a metal hose, you want to look for a hydroformed hose. And a general rule of thumb here on this slide, and every hose is different, but these are approximations. If I was to say a relative permeation rate of a metal hose is 1, it's a unitless value here. A post-sintered Teflon hose permeates about 10,000 times as much as a metal hose. Slow sintered is about 20, and Teflon hose is about 100. The basic impulse life, or the ability for the hose to withstand impulses in the core, go in the opposite direction, because essentially what we're doing here is we're making the hose softer as it goes down, which makes permeation higher, but impulse life longer. So it's again a trade-off. What's best for the application depends on what's important for the user, for the person installing and using the hose. Okay, moving on to reinforcement. So again, the core tube only withstands a couple atmospheres of pressure, about 30 psi, give or take. So it needs to be reinforced. Most applications are going to be more than 30 psi. And this is typically done with a braid, as you see in these pictures. And there's different kinds of fiber braids, and there's also quite a few different metal braids. So both come with their strengths and weaknesses, of course. Fiber's a little less expensive, and it's non-conductive if that's important. The metal braid, a little more expensive, but it's going to be stronger, higher temperature, and be conductive if that's what's important to the application. Sometimes it doesn't matter. So the braid's put on is actually pretty cool to watch. It's done very quickly, but when the braid is put on, what we're doing here is we're testing for pressure performance. So that 30 psi core tube now withstands 3,000 or however many psi, depending on the braid design. The braid also gives a lot of hoop strength to the hose. So just a core tube will kink very, very quickly, but as soon as that braid's put on, the braid now has a lot of hoop strength that allows for the core tube to bend without kinking. It needs to maintain flexibility, and this is an important feature, and it's very difficult to do sometimes because we want to give nice thick wires to our braid to increase pressure performance. But what that does, of course, is it decreases flexibility, makes the force to bend much higher. Same with the torsion strength. We're trying to increase the strength of the hose without minimizing the flexibility too much. And when a hose, I have a slide on it here, I'll show that later, but a hose wants to expand both axially and lengthwise, and the braid is there to withstand expansion in both directions. So moving on to that, that's what I'm trying to show with these pictures. If a braid angle is too small, my top pictures, so the braid is too shallow, what will happen is the hose wants to grow, again, both axially and lengthwise. But in this case, the braid is protecting against length growth, expansion, not axial expansion. So the hose will end up growing axially and shrinking lengthwise. This can be, of course, very dangerous because now the hose has a tendency to burst. The braid or the core tube will not allow for that amount of axial growth and it'll burst. So a too shallow braid angle is dangerous. If the braid angle is too steep in the bottom picture, the hose now will not grow axially, but it'll grow in length. And what this causes is a loss of containment on your end connection most times. And so again, the hose will burst, but in this case, it's bursting by separating from the end connection, which can be extremely dangerous. The hose can whip and have massive leakage. So braid angles need to be studied a great deal so that as a hose is pressurized, and each hose is different, of course, the hose doesn't grow axially or in length, and we call that the neutral braid angle that stops any hose expansion in either direction. It's a very critical item, and we take it very seriously at Swagelok. Of course, we measure our braid angles all the time when we get bulk hose to inspect. The third step is then the cover material. Various covers are available, and it all depends on what the user of the hose is looking for. In this picture, it's a silicone cover on the outside of a metal braided hose, but there's a lot of different types of covers to be used depending on what we're looking for. Most of the time, a cover is there to protect the user or protect the hose from the environment or from the application. In the case of these silicone covers in this picture, those are typically used for cleanability. But those are really the top two reasons to use a cover. And they're nice for us as well because we can mark the cover with pressure ratings and part numbers and things like that that allow for ease of use and asset management. One thing noted here at the bottom, a cover will never increase flexibility. The hose is not going to get more flexible when you put a cover on it. It can get a little bit less flexible. And it's also never going to be a pressure containment device. Permeation on a silicone cover hose, as you see here, is just as fast as without the cover. The cover is not holding back any permeation. It's going to permeate faster than the inner core. So it's really not doing any kind of leak containment or pressure increase for the hose. So the first reason here, cleanability. Many high purity applications, they need to wash down the hose, and a lot of times the braid can be fairly dirty. Braid wires, as a hose is bent, will shed particulate and be a bit on the dirty side when you handle the hose. So a nice silicone cover gives it cleanability and a nice clean outer surface. The next is to protect the hose, abrasion and crushing. On an extreme case, you see the picture on the left. Obviously, that hose is junk now, but before it got to that level, as those braid wires start to break, they can be very dangerous. They're, again, very thin wires and can cut people. But obviously, something was rubbing up against that hose, and with some protection on the outside of the hose, maybe this could have been avoided. The two most popular covers for this are what we call spiral guard, which is what you see in the middle picture, and those can be color coded. They just wrap right around a hose, and it provides a strong, durable, abrasion resistant cover. And then armor guard, which is a crush proof cover that we put on that makes it so you can essentially stand on the hose, jump up and down on the hose, maybe even drive over the hose in some cases, but it allows for a crush proof outer casing so that protects the inside of the hose and from any kind of damage. And then lastly, and probably one of the most significant or most common things we see as far as safety issues go with the hose are for hot hoses, but the same can be true with cold. So we see an increase in usage of insulation on hoses for a lot of high purity applications. Again, condensation on a chiller line is very important to avoid. And so in order to avoid that, we need to keep the temperature of the hose above the dew point. And to do this, we need to make sure the hose is insulated, because a lot of times the inner media is -20, -30, -40 degrees, and that will create condensation on the outside of the hose. So insulating the hose is the only way to avoid condensation in high purity situations. And then more commonly though, in hot applications, steam lines, things like that, hose can be very dangerous to touch. 200 degrees steam with a metal braid, if you touch that, you'll end up with a pretty significant burn. So again, insulation is needed to keep the outside of the hose safe to touch. And not all insulation is the same. What's used for cold applications is not what's best for hot applications. And so, insulation material can be better at different temperature ranges, and it's always important to know what the insulation is rated to and where it's supposed to be used. And this is an example of that. We do a lot of testing on our hoses for different levels of insulation. And the picture on the left, the graph on the left, is just showing the dew point of about 14 degrees Celsius and different temperatures based on different levels of insulation. So what we're trying to do here is just keep the temperature of the hose above the dew point, above the black line. And that's going to depend on how much insulation is on the hose and what the inside temperature is. And that's what we're trying to show in these graphs here. But again, it's a lot more complicated than just wrapping a hose with insulation. How much insulation is needed, what type of insulation is needed, is all very critical to getting the right performance. And then the picture on the right is an example of a hot application where you have a certain media temperature, steam or whatever it might be. And then how much insulation is needed to keep that hose in a safe to touch range, which typically is around 60 degrees Celsius or 140 degrees Fahrenheit, is typically thought of as safe to touch. So how much is needed to keep it below that temperature so that someone going to grab the hose won't end up with a burn. And then lastly, for covers, this isn't really a cover, I suppose, but it's a nice accessory that goes on the outside of a hose. It's an anti-lash cable. If a hose were to fail in any way whatsoever, where it separates from the end connection, the hose in a high pressure application can whip around very drastically, causing a very unsafe situation. So many times for high pressure situations, we can put a cable. Cables are used on hoses that are tied down to equipment. So if the hose were to burst or separate or something drastic happen to the hose, it won't whip around and cause personal injury. All right, moving on to the last step, end connections, and this is relatively straightforward. Of course, end connections are typically used that fit with the rest of the system, right? So whatever's needed for that particular application, whether it's a standard tube adapter, pipe fittings, high purity VCRs, whatever it might be. But it's important to understand that the end connection, of course, needs to be able to be used. Sometimes it can be difficult when people don't think that, hey, I have a threaded connection on both sides. How do I thread a hose in without causing torsion? So those things need to be thought through if it's a pipe thread, for example. One key aspect here is different end connections are different lengths. And so when you're deciding on your final hose part number, you have to know if that hose manufacturer is listing an overall length or a live length. I'll tell you, in our case, we list overall lengths, but you need to take into account how much that end connection takes away from the live length of a hose. Of course, the live length is the part that's flexible. So if you have a long end connection, you can take considerable distance away from the live length or the flexible length of the hose. That's usually pretty straightforward and a bit obvious, but we've seen it forgotten about when people spec in a hose part number. And then, of course, there's other options, and these are all listed by the hose manufacturer, different tags. We always say, make sure you have preventative maintenance plans for hoses. It is a wear item. So in order to do that, hoses need to be properly marked and tracked. Best way to do that is with a permanent tag. We have various ways to do that. We can help you out if you need any assistance with that. Okay, I think we have some real quick practical examples, and then we're going to go through a couple questions if we have any. So real quick, again, I won't open this up to the group necessarily. We'll just talk through it. But in this particular application, let's say it's a hydrogen service application, low pressure, low temperature, and let's say a very strong vacuum is required. So what we want to do here is we want to look at hydrogen and understand that's a tiny molecule. It's going to be in gas phase, and we want a strong vacuum. These two indicators really lean us towards all metal, although with hydrogen, you need to be a little bit careful with a metal hose, especially with stainless, just because of hydrogen embrittlement, but it most of the time works out just fine. But the metal core will stop any permeation of what could be potentially dangerous with hydrogen. And again, metal hose will withstand an extreme level of vacuum, which in this case we were looking at. The temperature and pressure rating of a metal hose are well beyond what we list here in this application, but with hydrogen, I think it's the best way to go. And then a second one here, just real quick, upper level stuff, a corrosive chemical, again, low pressure, low temperature. The key with this not only is corrosive, but must be easily cleaned. So that's leading us towards a smooth bore. And again, it's low pressure, system test is needed, but the cleanability of a Teflon core, especially with corrosion in mind, really lead us towards a Teflon smooth bore hose. It will be easily washable. Okay. I know we are running close to the end of time here, so my apologies for going over, but again, I appreciate everyone joining in for part 2. If you're looking for this material or looking for material from part 1, please reach out to your Swagelok contact. And we have different levels, different material for this if you want to dive in any deeper. We have a hose essentials class, which is a few hours long that your Swagelok contact can help set up for you. We have hose advisors at each sale and service center and field engineers that know a great deal of this material and can help out if needed. And then of course, we're going to have session 3. And that brings us to what session 3 will be. It'll be December 10th at 11 a.m. Pacific time, I believe, right? And we're going to go into more detail on static dissipation versus conductivity. That's a very misunderstood topic. So we're going to spend some time on that, go into a little more detail on permeation, and look at various core tube failures, including what happens with different metal hoses. And Jen, with that, I'd like to open up to questions. Again, I know we're a little bit over time, but if there's any, I'm happy to stay around as long as anyone else wants to.
Yeah, that's great, Doug. Thank you. We do have a few questions here. The first one is specific to Teflon core hoses. Will atmosphere permeate through those Teflon core hoses if the hose is under vacuum less than or equal to 28 INHG?
inch of mercury. Yeah, yes, it will. Great question. Actually, permeation is a weird thing. It will permeate. Atmosphere will permeate into a pressurized hose, actually. So if you have a pure nitrogen, air will permeate into that hose, even if it's under pressure. The pressure doesn't stop air from permeating in, oxygen from permeating in. Permeation happens in both directions. So nitrogen will be permeating out, at the same time oxygen will permeate in. And we've run into troubles with that when people use a Teflon hose for a argon welder, for example. Oxygen gets to the end of the hose. So a metal hose is needed to stop that permeating into the hose.
Great. Is there a maximum recommended pressure for Teflon core hoses when using toxic corrosive gases, specifically with respect to permeation?
Right, so that's going to come down to the permeation rate. I would certainly recommend going with that post-centered version, which we can help you identify which hoses are post-centered and which hoses are slow-centered. So with a post-centered hose at 3,000 psi, that same 1 foot long hose permeated about it was about 4 cc's per hour. versus liters per hour. So it depends on the toxicity, I guess is the word, of what the gas is. But you'd have to determine how well the area is vented, and if 4 cc's per foot is okay or not. And we can help you with permeation rates if you have a more detailed question on that.
Okay. We also had a question about pressure ranges in the figures for each type of hose. Is the catalog the best place to kind of refer to Swagelok specific for that?
Catalog is the best way to get those levels. In general, we have Swagelok has metal hoses that get up to the 6,000 psi range, and Teflon core hoses that get up to the 3,500 range. It is possible to go higher on both. It just matters of how many braids to put on. The more braid layers, the stiffer the hose, more expensive the hose, but the higher the pressure.
Okay. There's a question about spiral covers in the catalog. Do we sell what would be considered a spiral catalog, and where would be the best way to find information on those?
The spiral guard, I believe, is what the question is referring to.
That sounds right, yeah.
Yeah, so the spiral guard is in the catalog. It's a really pretty simple product, really, and easy to put on, but it is great for abrasion resistance. And there's various colors if you want a color code based on whatever the media is or anything you want. And again, the sales and service centers can help you identify which is best for you on that one.
Okay, and a few more coming in. Is there a recommended minimum pressure to use a cable connection with a flexible hose to prevent hose whipping?
Yeah, we get into that quite a bit. We've done a lot of testing. We'd be happy to share some videos of causing a hose failure to see what kind of whipping action happens at various pressures. And I'll say that anything above about 1,000 psi is pretty drastic whipping. It's pretty scary. We do see some of our customers specify hose cables on anything above 200 psi, which is fairly low. It's not really drastic whipping, but anything above 1,000 can get a bit scary.
Sorry, I was muted. Any general advice on what materials to use in a high radio frequency environment where end connections are RF hot, but the hose cannot be conductive?
Yeah, we're going to get into that one. That's something that, I'm sorry, go ahead.
Just to expand on that, they said they use a nylon core 7R series, and they have issues with degrading of the core, causing clogging in the end connectors. The media is water. Oh,
interesting. I'm not familiar with that problem happening, but it's maybe something we can dive into. But yes, we do have some hoses. I would recommend a Teflon core hose. And there's a couple different options we have, and we're going to get to that more in session 3. But one thing we see is that a Teflon core hose in those applications will have static dissipation and therefore cause problems with getting leaks. Static dissipation is very different than conductivity. And we were able to convince some users to switch to a static dissipative, non-conductive hose with a fiber braid. And even though they were concerned about the static dissipation being conductive, it's worked out wonderful for them. And I can include an example of that in our next Tech Talk.
Great. Can non-metal hose be used for applications where flammability is a concern?
It can. It would obviously be not quite as safe. So I think it depends on how much of a concern, I suppose, is the way to answer it. The Teflon, of course, will fail in a flammable environment. So it's not necessarily recommended, but we could talk about how to use a silicone cover or something to increase protection on that. Great.
And is a safety cable option included in the catalog?
It is not, but we can get you information on that. I can send that out, Jen, to you guys, and you can share it with the people on the call. That is something that we're looking to do. We have it, and we're looking to include that in their catalog in the next few months, but we can get you something now.
Yeah, we can send that out to him. So if everyone, just in case you didn't see it, we will follow up with you if you registered for the webinar with a recording. and the Q&A here at the end. If you need to contact us specifically, I have a link at the top of the chat that will help you identify your local sales and service center for Swagelok if you don't already know who that is. I have one more question here. So Jim asked, does permeability in Teflon hose increase or decrease with the hose diameter?
It increases, but it's not quite that simple. And we'll get into a little more detail on that as well. But permeability is a direct correlation to surface area. So if you imagine a 1-inch hose is going to have a lot more surface area than a 1/2-inch hose, almost 4 times actually. But at the same time, it decreases with the core tube thickness. So a 1-inch hose has a thicker core tube than a 1/2-inch hose. So it's not exactly 4 times because of the thicker core tube, but it will increase. And we can show some of that data too if you're interested next time.
Great. All right, that looks like all the questions that have come in. So we will go ahead and wrap this up. Thank you so much for everyone's time and for your presentation, Doug. We greatly appreciate it. And everyone have a great day.
Yeah, thank you. Thank you, everyone.